Okay, good morning. Yesterday we have discussed about this. Okay, materials can be divided into three categories: conductors, semiconductors, and insulators. So there are three types of materials that we have studied in yesterday's class. Okay, conductors are having a good amount of conductivity, whose energy gap between the valence band and the conduction band is equal to 0. Resistance is very low. Resistivity is also very low. Whereas in the case of semiconductors, there is an energy gap between the valence band and the conduction band. The energy gap is very small, less than 3 eV. And the resistance of semiconductor is little bit higher compared to this. Okay, resistivity is also more than this. Whereas in the case of insulators, valence band to conduction band, there is a huge energy gap. And in insulators, resistance is very high. Resistivity is also very high. These ideas we have already come across in yesterday's class. Okay, conductors, semiconductors, and insulators. Now in today's class, what is that? So you see that semiconductors only we are supposed to study. We are going to study about semiconductors. Okay, we have to study about semiconductors. Right. Under semiconductors, it has been divided into two categories. Semiconductors, we are going to study about the conductors under electricity chapter. Insulators we are not going to study. In between state is called by the name the semiconductors. Semiconductors now onwards we are supposed to understand. Only about semiconductors. This chapter is representing for semiconductor concepts only. Okay, in the case of semiconductors, it has been divided into two categories. Okay, one is intrinsic semiconductor. Intrinsic semiconductor. The other one is extrinsic semiconductor. So there are two types of semiconductors: intrinsic semiconductor and extrinsic semiconductor. Okay, superconductors, semiconductors can be divided into two categories. One is intrinsic semiconductor, the other one is extrinsic semiconductors. Okay, semiconductor, intrinsic, extrinsic. Intrinsic semiconductor means it is pure semiconductors. Intrinsic means it is a pure semiconductor. Extrinsic semiconductor means it is an impure semiconductor. Impure semiconductors. Okay, there are two types of semiconductors: intrinsic semiconductor and extrinsic semiconductors. In the case of intrinsic semiconductor means it is a pure semiconductor. Pure semiconductor where the current carriers, maybe the electrons, freely available electrons for the conduction from one atom to another atom, is almost equal to 0. Of course, at 0 Kelvin. At 0 Kelvin. Now, let us consider the concept here now. An intrinsic semiconductor example. Some examples I will quote it here. Example, either it is germanium or it is silicon. Intrinsic semiconductor example, either it is germanium or it is silicon. It is a pure semiconductor. Intrinsic semiconductor means it is a pure semiconductor. Example, germanium, silicon. Then what do you mean by these extrinsic semiconductors here? As you are adding some impurity here, it is a pure. If you are adding impurity here, addition of impurity, then it is called by the name extrinsic semiconductors. To an intrinsic semiconductor, when it has been added some amount of impurity, then it is converted in the form of extrinsic semiconductor or impure semiconductors. Then this addition of impurity is called by the name. This is called by the name doping. Okay, what do you mean by doping? The addition of impurity to the intrinsic semiconductor to make them as extrinsic semiconductor, that is called by the name the doping. The added impurity is called by the name the doping agent. Doping agent. This process is called by the name the doping. It's a process of addition. This is the process of addition of impurity. The process of addition of impurity is called by the name the doping. And the added impurity is called by the name doping agent. This is called by the name the doping agent. So the one more question here now. What do you mean by doping agent? Doping agent, it is an added impurity to convert an intrinsic semiconductor to extrinsic semiconductor. If you are converting an intrinsic semiconductor to extrinsic semiconductor, if you are adding the impurity, that added impurity is called by the name the doping agent. That is called by the name the doping agent here. And now, the doping agent, there are two types of there. Under the doping agent, there are two types of doping agents. One is pentavalent impurity. We are adding pentavalent impurity, and we are adding trivalent impurity. So there are two types of doping agents. One is pentavalent impurity or doping, that we are going to do it. The other one is trivalent impurity. We are also adding that. Trivalent impurity can also be added here. Pentavalent impurity can also be added here. Therefore, the doping agent, there are two types of doping agents. Pentavalent doping agent, trivalent impurity. There are two types of impurities. Here, whatever we are adding, the process of addition of impurity to the intrinsic semiconductor to convert in the form of extrinsic semiconductor is called by the name the doping. Doping agent means whichever we have added as an impurity, either pentavalent impurity or trivalent impurity, is called by the name the doping agent. Now, which are the pentavalent impurity? Usually we are adding here. Pentavalent impurity, either we are going to add as a pentavalent impurity antimony that we are adding. Yes, B means antimony. Arsenic we are adding, or maybe we are adding phosphorus. Anyone. All are pentavalent, having the 5 valence electrons in its outermost orbit. Arsenic is also having the 5 valence electrons in its outermost orbit. Phosphorus is containing 5 valence electrons in its outermost orbit. It's a valence electron. Trivalent impurity we are adding is either it is indium, or it is gallium, or it is aluminum, or it is boron. These are the materials. These are the elements. Trivalent impurity usually either indium, gallium, aluminum, boron. They are acting as trivalent impurities. This trivalent impurity, any one of this one we are adding here. Pentavalent impurity, either it is antimony, arsenic, okay, phosphorus, that we are going to add. Okay, next idea. How much that we have to add as a doping means we are supposed to add this impurity. We are supposed to add the impurity. How much we have to add the impurity? If the germanium is 10 to the power 8 number of atoms, then either this or this we have to add only one atom. So whatever we are adding the impurity here, it is in the ratio of 10 to the power 8 is to 1. This is 10 to the power of 8 is to 1. In that ratio that we are supposed to add. Okay. So how much you want, you cannot add it here. No. With a basic proportionate, we are supposed to add the impurity. If the original atoms are germanium and silicon, germanium or silicon, maybe 10 to the power of 8. Either it is pentavalent or it is trivalent, any one impurity that is said to be equal to 1. In that ratio only, we are supposed to add the impurity. It should not be more than this, or it should not be less than this. Like that, we are supposed to add. So with this ratio, we are supposed to add. Okay. This is how much that we are supposed to add. Number of the atoms, impurity atoms, how many that we are going to add, that is said to be in the ratio of 10 to the power of 8 is to 1. Next one, if you are adding this, what will happen? If you don't add this one, what will happen here? The question is, why we are supposed to add the doping agent? If you are adding the doping agent, why we are supposed to convert that intrinsic to extrinsic here? So meaning, semiconductors can be divided into two categories, intrinsic and extrinsic. Intrinsic means pure semiconductors, extrinsic means impure semiconductors. Example for pure semiconductor, it is either germanium or it is silicon. If you are adding some amount of impurity, then it is converting in the form of extrinsic semiconductor. Now, the addition of impurity to the intrinsic semiconductor to make it as extrinsic semiconductor is called by the name of doping. And the added impurity is called by the name of doping agent. There are two types of doping agents. One is a pentavalent impurity, the other one is trivalent impurity. Pentavalent impurity, which must be containing the 5 valence electrons, either antimony, arsenic, phosphorus. Trivalent impurity is having the trivalent, it is having the 3 valence electrons, either it is indium, gallium, aluminium, boron. Then we are supposed to add this as impurity to the intrinsic to make it as extrinsic. What ratio we are supposed to add? If the original atoms are 10 to the power of 8, then the added impurity is said to be 1. In that ratio, we are supposed to add. Now I said, the question, if you don't add the impurity, what will happen? Means, what is happening in the case of intrinsic semiconductors? What is happening? In the case of intrinsic semiconductor, just I will going to take up only the intrinsic semiconductors now. What is happening in the case of intrinsic semiconductor? What is happening here? Intrinsic semiconductors. In the case of intrinsic semiconductors, means pure semiconductors, you choose any one here, either germanium or silicon. Germanium or silicon, anyone we can choose. You select anyone, no problem. I will consider germanium crystal. Let us consider germanium crystal, which contains germanium atoms. Germanium crystal is containing germanium atoms. If I'm writing germanium atoms one by the other, I can show it like this, which is tetravalent. Germanium atom is tetravalent. Means it is containing 4 valence electrons. Each germanium or each silicon which is containing 4 valence electrons. I will show it here. This is germanium, one atom having 4 valence electrons. These are the 4 valence electrons germanium is containing. Neighboring, one more germanium atom is there. Like this. This is another germanium atom. 4 valence electrons for this germanium, 4 valence electron for the other germanium. Next one, it is containing one more germanium atom here. Like this, another germanium atom. Like this, it will continue. It will continue, I said. This is germanium. This is one more germanium. Like this, the crystal, it will continue. Germanium, like this. Here, one more germanium. Like this, 4 valence electrons. Every germanium atom is containing 4 valence electrons. As a crystal, if you are choosing, this is a crystal if I'm considering, then in that crystal, number of available free electrons is equal to 0, because this valence electron of one germanium atom the valence electron of another germanium atom. They want to make it as octet. You know about chemistry knowledge. According to that one, we can say this one and this one, they are sharing the electrons. The sharing of electrons between the two atoms is called by the name the covalent bond. Therefore, one atom of germanium to another atom of germanium, here to here, there exists a covalent bond because of sharing of the electrons. Here also, there is a covalent bond. Here there is a covalent bond like this. The covalent bonds are going to get forming here. Like this. Everywhere covalent bonds are present. As the covalent bonds are present here, all of us, we know about that covalent bond is a stronger bond. Not so easy to remove that. Therefore, as the covalent bonds are existing here, number of free electrons in this case, number of free electrons available for electrical conduction, that is equal to 0. No free electrons are available because all the electrons are involving in the covalent bond. If at all, if you want to get the number of free electrons here, we have to break the covalent bond. As you are breaking the covalent bond here, we require energy. The crystal requires energy here. So these are the germanium crystal is present. The germanium crystal is containing 4 valence electrons. All the 4 valence electrons, they are involving in the 4 covalent bonds. Hence, the number of free electrons available in an intrinsic semiconductor, it is equal to 0. If it is equal to 0 here, it cannot conduct. It cannot conduct. At what temperature? That is also important here now, at 0 Kelvin. At 0 Kelvin, all the covalent bonds are present here. Number of covalent bonds are existing here now. Because of that one, no free electrons are available. Hence, the germanium in its pure state, it is not conducting at 0 Kelvin. At 0 Kelvin. But this particular material, it is not kept at 0 Kelvin. Usually, we are keeping in the atmosphere. Atmosphere, maybe Indian standard condition, maybe it is equal to around about 30 degrees centigrade, 35 degree. Even in the summer season, maybe 40, 42 degrees centigrade, it is said to be existing. As the temperature is acting here, let us assume that atmosphere temperature is acting. As the atmosphere temperature is acting here, heat energy, it is activated here. Because of that one here, 1 or 2 covalent bonds are breaking up. As the covalent bonds are breaking because of the temperature, okay, here I can say some germanium atoms are collapsing their covalent bonds. Covalent bonds are collapsing. Not all the covalent bonds, some covalent bond. Maybe this is the covalent bond is breaks up like this. Here covalent bonds are present as it is. Like this. It will continue. This covalent bond is present. This covalent bond is present. Here also is present. Here also is present. Everywhere is present here like this. It will continue. But this covalent bond is broken. It has been breakdown. Covalent bond, it has been broken down. As the covalent bond, it has been breaks up. Now, we are getting 2 electrons here. Let us consider 1 electron if it is shifting from here to here like this, moving. If this electron is moving from here to here, I can say it is a free electron. That is free electron. But the number of free electrons are less because of this temperature. Because of this temperature, this germanium or silicon containing the 4 valence electrons, all the 4 valence electrons, they are involving in covalent bonds. Due to this temperature, some of the covalent bonds are breaking up. If 1 or 2 covalent bonds are breaking up, then free electrons is available. That electron is moving from one atom to another atom, one atom to another atom. This free electron starts to move. Once this is moving from here to here, here there is a vacancy for the electron. Here free electron is coming. Here there is a vacancy for the electron. The free electron which is moving here, and this vacancy must be packed up. This vacancy must be going to get closed down by using another electron. This another electron moving from here to here and occupying here. Before occupying, here there is a vacant space. If there is a vacant space is present here now, that vacancy is called by the name hole, H-O-L-E. Due to this electron, if it is moving, if this electron is moving from here to here like this, now here there is a hole. I can say this is called by the name the hole. Hole, there is a shortage of an electron. There is a shortage of an electron, hence it is said to be having a positive charge. Means there is a shortage of an electron. Because that electron, it has been moved from here to here. This is the electron, extra electron. Because the covalent bond is breaking up, one electron is moving here, that is a free electron. Due to that movement of that free electron, here there is a vacancy is created for the electron. The vacancy is called by the name the hole. Hole carries the positive charge, electron carry the negative charge. If the electron is present here now, the hole cannot be existing. Now, if this electron is moving from here to here, then covalent bonds are forming here, but here there is a hole. Again, electron is shifting from here to here, hole is present here. Like that, hole is also moving, electrons are also moving. Due to electrons, whatever it is moving, and hence there is a current. Holes are moving, due to that one there is a current. But unfortunately here, number of electrons is equal to number of holes. Electric current due to the electrons, electric current due to the holes, they are equal to each other. In this case, number of electrons is equal to number of holes. How many holes are created, that many number of electrons are present. How many number of electrons are shifting here, that many number of holes are created. Hence, electric current due to the number of electrons is equal to the electric current due to the number of holes. These two are equal to each other in the case of intrinsic semiconductor. Since electric current due to the electrons, electric current to the holes, they are equal to each other. It is therefore intrinsic semiconductor, it has no use. We cannot use this one for our electronic circuits because current flow due to the electrons, current flow due to the holes, they are equal to each other. Hole current, electron current, they are equal to each other. Number of holes, number of electrons, these two are equal to each other. Hence, we cannot use the intrinsic semiconductor for our electronic circuits. Due to that one, we are supposed to switch over from intrinsic semiconductor to extrinsic semiconductor. Because conduction is very less under normal temperature. Conduction is equal to 0 at 0 Kelvin. Therefore, a semiconductor at 0 Kelvin is acting as an insulator. A semiconductor at 0 Kelvin, it is acting as an insulator. As the temperature increases for a semiconductor, then conductivity is also go on increasing. So this is about this intrinsic semiconductor. Now I suppose to start with extrinsic semiconductor. It is not valence bond, no, cannot be existing. Valence band, that is. Okay, it is a valence band. It is not valence bond. You are showing as valence bond. This is covalent bond. Covalent bond. Bond is different, band is different. Valence band, due to the valence electron, valence band. Energy due to the valence electron, valence band. Due to the conduction, conduction band is present. So that one we have discussed already. This is how the crystals are present, how the atoms are arranged inside the crystal. Then if you are adding some amount of extra energy here in the form of temperature or electricity or something, what is happening, we have to think. This is under normal temperature. Maybe 30 degrees centigrade, 25 degrees centigrade, if it is said to be existing here, then one or two covalent bonds are breaking up. Therefore, you are going to get electron hole pair. As the electron hole pair is going to get produced, pair, electron hole pair is producing here. Due to that one, electrons are shifting from one atom to another atom. Holes are also moving here, but unfortunately, number of electrons is equal to number of holes. Current due to the electrons is equal to current due to the holes. These two are equal to each other, and also it is very small amount. Therefore, we cannot use the intrinsic semiconductor for the electronic circuits. Therefore, we are supposed to switch over to extrinsic semiconductors. Now we are supposed to start with extrinsic semiconductors concept. Now next one, extrinsic semiconductors. I told you already, we are having intrinsic semiconductor. We want to get extrinsic semiconductor here. If you want to get the intrinsic semiconductor to extrinsic semiconductor, we are supposed to add the impurity. Addition of impurity. We are supposed to add the impurity here. The addition of impurity, which is that? This extrinsic semiconductor, either it is germanium or it is silicon. The addition of impurity, either it is pentavalent or it is trivalent. Either it is pentavalent or it is trivalent. Now we are supposed to think about that extrinsic semiconductor. Here, there are two varieties of it, meaning intrinsic semiconductor means germanium or silicon. As you are adding a pentavalent impurity, as you are adding pentavalent impurity, you are getting extrinsic semiconductor. That extrinsic semiconductor is called by the name N-type semiconductor. You are going to have N-type semiconductors. Therefore, I can say extrinsic semiconductor can be divided into two categories. One is N-type, the other one is P-type. Small letters. N-type, P-type semiconductors. How to get N-type semiconductors? To an intrinsic semiconductor, we are adding a pentavalent impurity. Then we are going to get an extrinsic semiconductor called by the name the N-type semiconductors. Now, let us consider intrinsic semiconductor, either it is germanium. Okay, that one afterwards we had to think about that. Okay, Monisha, you listen first. Afterwards you can ask, even tomorrow's class. I mean, day after tomorrow also you can ask. Intrinsic semiconductor, germanium. If you are adding pentavalent impurity, then resulted extrinsic semiconductor is called by the name N-type semiconductor. For an intrinsic semiconductor, as you are adding a trivalent impurity, okay, two varieties of impurities are there. Pentavalent, if you are adding, the resultant extrinsic semiconductor is called by the name the N-type. If you are adding a trivalent, then it is called by the name P-type semiconductors. P-type semiconductors. So therefore, extrinsic semiconductor can be divided into two categories. One is N-type semiconductor, the other one is P-type semiconductor, depending upon which added impurity that you have used. If you are adding a pentavalent impurity, then we are getting an extrinsic semiconductor, which is N-type. If you are adding a trivalent impurity, then we are going to have P-type semiconductors. Now, at least N-type semiconductor, today let us have a discussion. Still 6 minutes time is there. Okay, first let us think about that. N-type semiconductors means it is an extrinsic semiconductor. N-type semiconductor is an extrinsic semiconductor. What is happening here? I told you, for an intrinsic semiconductor, to enhance the conductivity, to increase the conductivity, we want to raise the conductivity by adding a pentavalent impurity. Intrinsic semiconductor conductivity is very low. Intrinsic semiconductor, number of electrons is equal to number of holes. As you are adding a pentavalent impurity, what is happening here? As you are adding a trivalent impurity, what is happening here? You are supposed to learn these questions we are asking at the time of examinations. Write the differences between N-type semiconductor and P-type. Explain the N-type semiconductor or P-type semiconductors. Like that, we are asking for about 3 marks question. Okay, first idea. What do you mean by N-type semiconductor? One more question. What are N-type semiconductor? To an intrinsic semiconductor like that of germanium, example, if you are adding a trivalent impurity, if you are adding a pentavalent impurity, we are getting an extrinsic semiconductor which is called by the name N-type semiconductor. To an intrinsic semiconductor like that of germanium, as we are adding a trivalent impurity, then we are going to have P-type semiconductors. First one, in the case of N-type semiconductors, what is happening? N-type semiconductors. Okay, in the case of N-type semiconductors, okay, basically it is germanium. This is germanium crystal. I will write it here, just you see that. This is germanium crystal. For this germanium crystal, we are supposed to add any pentavalent impurity. Let me consider arsenic, it has been added. Now, the resultant one is called by the name N-type semiconductor. Okay, understood the concept? For a germanium crystal which is containing germanium atoms. A germanium crystal containing germanium atoms. If you are adding arsenic, arsenic is also an atom. Atom is electrically neutral. This is electrically neutral. One more question, it has been framed. This is also electrically neutral according to Bohr's theory. An atom is electrically neutral. For a neutral crystal, electrically neutral crystal, which is containing germanium atoms, each atom is electrically neutral. If you are adding one more atom, that is said to be arsenic as a pentavalent here, as a pentavalent impurity, it has been added here. That is also an atom which is electrically neutral. Therefore, N-type semiconductor, which is containing the atoms here and atoms here now, and hence this is also electrically neutral. So one more question, it has been framed already in your previous years of examination. Okay, what N-type semiconductors, are they electrically charged? Answer is no. The question is why they are not electrically charged? Because if you want to get the N-type semiconductors here, for a germanium crystal which is containing germanium atoms, which are all electrically neutral germanium atoms to which we have added electrically neutral arsenic atom. Therefore, the resultant one is N-type semiconductor, which are also electrically neutral. This is electrically neutral, this is electrically neutral, hence this is electrically neutral. One more question. But what is happening in the case of N-type semiconductors? It is a basic idea that I said. Now let us verify the concept, how it is electrically neutral, what is happening here and other things. Now let us consider germanium crystal. As you are adding germanium crystals, one atom of arsenic, I told you already, we are supposed to add this one in the ratio of 10 to the power of 8 is to 1. 10 to the power 8 atoms of germanium, 1 atom of arsenic we are supposed to add. The ratio between here to here is 10 to the power 8 is to 1. These atoms are 10 to the power of 8. Arsenic atom, whatever we have added, is only 1. As we are adding like this, what is happening here? This is arsenic. Arsenic is containing 5 valence electron. I will write the 5 valence electron with an into mark here. Into mark representing the electrons belongs to arsenic. The electrons belongs to arsenic. I have written with into mark. Okay, 5 valence electrons. Arsenic is a pentavalent material. It is a pentavalent atom which is containing 5 valence electrons. Then if you are adding arsenic, 1 atom of arsenic to germanium crystal, then it has been surrounded by this one. There are germanium crystals are present, germanium atoms are present. Inside the germanium crystal, atoms are present here. I will show that one also here. To understand about this, this is germanium electron, this is germanium electron dot, this is germanium atom. Dot representing the electrons belongs to germanium. This is a dot, electron belongs to germanium. Like this. Like this is present. Due to this here, this germanium atom, this arsenic atom, they are sharing an electron. Here, germanium atom electron, this is arsenic atom electron. These two are sharing to make it as octet. These two are sharing here. Here also sharing. Covalent bonds are forming. It will continue like this. Covalent bonds are present here. Germanium, germanium like this. If you want, I will show it here like this. Like this. Here also germanium. Here also germanium. It will continue. It will continue like this. Okay. Meaning for the germanium crystal, we have added a small amount of 10 to the power of 8:1. That ratio, it has been added the arsenic. Arsenic is a pentavalent impurity. Pentavalent means it is containing 1, 2, 3, 4, 5. Out of the 5 valence electron, arsenic is forming 4 covalent bonds with the neighboring germanium atoms, but 1 electron is freely available, which is not involving in the covalent bond, whose binding energy is less. This binding energy is more because of covalent bond.